right. Thank you so much for working with me on lectures like this. We will have a chance, I think, to briefly discuss Chapter 13 on Tuesday, April 11th, when we return to back to class again. I'll be there. So today we're going to talk about Section 13.7. It's called Tangent Planes and Normal Lines. And you can see the objectives here. We want to find equations of tangent planes and normal lines to surfaces, and that's going to be the main thing. I mean, it's the title after all. But we will also look at the angle of inclination of a plane in space, and we'll compare these gradients. And before we could really talk about them much, let's look at the definition of this gradient of capital F. For any surface, S, given by z equals f of xy, we can convert to the general form by defining capital F as a function of three variables. Capital F of xy z equals f of xy minus z. Because little f of xy minus z equals 0, we can consider S to be the level surface of capital F given by capital F of x, y, and z equals 0, right? So all we're doing is setting the function equal to 0, and now it's a function of three variables rather than just the two. So we could take a look at a level surface, capital F of x, y, z equals 0. If we're given capital F of x, y, z equals 36 minus x squared minus y squared minus z squared. Well, if I wanted to describe this, I would remove it from the capital F, right, the general form notation. I would add x squared, y squared, and z squared to both sides. And then it's easier to see in the black, we have a sphere centered at the origin of radius 6. Right here, it might not be quite so obvious, but when we set it up as an equation of three variables that we're used to, it's really quite straightforward to see what it is. All right, so one of my favorite pastimes back when I was a consumer of alcoholic beverages in great quantities was pool. And pool, all about math and physics. All right, so when it's stationary, and the three ball here, the three ball is going to be our stationary ball, is struck at a point P on its surface. It moves along the line of impact determined by P and the center of the ball. All right, so it depends on where we hit it, and it depends on the center. The impact can occur in two ways. When the cue ball is moving along the line of impact, it stops dead and imparts all of its momentum to the stationary ball, as shown over here on the left, right? So as the cue ball strikes the three ball, the cue ball stops, and the three ball continues in the line of impact, right? The what's called the stationary ball. The momentum is what did it just say? Imparted to the other ball. Okay, but what if we're not hitting directly in the line of impact, right? A glancing blow. When the cue ball is not moving along the line of impact, it's deflected to one side or the other and retains part of its momentum. The part of the momentum that is transferred to the stationary ball occurs along the line of impact. So if you come at the red ball at an angle, notice the angle that the angle of incidence equals the angle of reflection. It's going to be a nice little return here on where the line of impact will go. Wow, I said that so wrong. I'm going to keep rolling though. This line of impact is called the normal line to the surface of the ball. Okay, so the normal line. Yep, moving on. Let's look at a surface. This surface, given by S, at a particular point, x sub 0, y sub 0, z sub 0, with capital F of x, y, z equals 0. So we have a normal and we have a tangent. So let's let F be differentiable at the point x naught, y naught, z naught on the surface S, given by capital F of x, y, z equals 0, such that the gradient of capital F at the point is not 0. Okay, so the plane through that point P that is normal to the gradient is called the tangent plane to S at P. The line through P having the direction of the gradient of capital F is called the normal line to S at P. So we're looking for planes and we're looking for lines. We have our gradient, we have our normal line, and we have our tangent plane, right? It's in only one spot, normal line. Okay, for the rest of this discussion, we will assume that the gradient of capital F is non-zero at any specific point is non-zero unless stated otherwise. All right, so in all the examples, assume it's not zero unless they tell you specifically, hey, this is zero. Okay, let's look at the equation of the tangent plane. So if capital F is differentiable at an initial point, x naught, y naught, z naught, then the equation of the tangent plane to the surface given by capital F of x, y, z equals 0 at the initial point is, a little sonic for me, the partial derivative of capital F with respect to x evaluated at the point multiplied by x minus x naught. The partial derivative of capital F with respect to y at the initial point multiplied by the change in y, right? It's always times a change, partial derivatives, changes. And then the partial derivative with respect to z at the point times z minus z naught, right? So this is very repetitive, very standard, equals 0. So we know how to write the equation of the tangent of the plane if we have a point and we have our capital F of x, y, z, which is equal to 0. So let's give this a shot. Find an equation of the tangent plane to the surface at the given point. It's equals x squared plus y squared plus 3 at the point 2, 1, 8. Equation of the tangent plane. So this is what I'm looking for. So I'm given z equals x squared plus y squared plus 3. My first step, I'm going to find capital F of x, y, z by subtracting z from both sides. Capital F is equal to x squared plus y squared plus 3 minus z. Now the partial derivatives, right? Using this function, the partial derivative with respect to x, this is the only term with x's, derivative is 2x. Partial derivative with respect to y, this is the only term that has a y, derivative is 2y. Partial derivative with respect to z, this is the only term that has a z, derivative is negative 1. Now we can find these partial derivatives, but now we need to evaluate, right? We're looking for the tangent plane to the surface at a point. So we need to evaluate the partial derivatives when x is 2, 2 times 2 is 4, when y is 1, 2 times 1 is 2, and when z is 8. Negative 1 doesn't care what z is. Negative 1 is just negative 1. Now that we have the values of the partial derivatives, we can set up our equations. We'll have partial derivative with respect to x is 4 multiplied by x minus 2, the initial point, the x coordinate of the initial point. Partial derivative of y is 2 times y minus 1. Partial derivative of z is negative 1 times z minus 8. And after we collect like terms, we'll have 4x, 2y minus z. Check that the constants work out. We'll have a plus 2 on the other side. We could always rewrite this as 4x plus 2y minus 2 equals z if we wanted to rewrite it back in the form that it was originally. All right, let's do that again. We're going to find an equation of the tangent plane to the surface, x squared minus 2xy plus y squared, at the point 1, 2, 1. First step, we subtract z from both sides. I'm going to let z equal f of xy. Subtract z from both sides to form our capital F function. Once we have our capital F function, we find the partial derivatives with respect to x. I'm looking at these two terms. Derivative of x squared is 2x. Derivative of minus 2xy is just minus 2y, right? X is our variable, don't care. Partial with respect to y, we only need these two terms. The derivative is minus 2x plus 2y. Partial derivative with respect to z, the only term that involves a z is right here, a minus z, so that has derivative negative 1. You'll see this fairly common theme. Very common. So if we evaluate at the point when x equals 1, y equals 2, when x is 1 and y is 2, we'll have 2 minus 4, which is negative 2. When x is 1 and y is 2, we'll have a negative 2 plus 4, which is a positive 2, and z is hanging out being negative 1. How do we write the equation of the tangent surface? Negative 2 times x minus the point, the x coordinate of the point. Positive 2 times y minus the original y coordinate of the point. Minus 1 times z minus the original z coordinate of the point equals 0. And when you collect, you have negative 2x, positive 2y, minus 1z. Add up all the values and we'll have a 1 on the right-hand side. Okay, so those two examples, Very similar. Now, this is going to look even more familiar. So we're going to look at xy minus z equals 0 and the point -2, -3, 6. First thing we're going to do is find an equation of the tangent plane to the surface at the given point. And that's what we just did in the previous two examples. Then we're going to find a set of symmetric equations for the normal line to the surface at the given point. Okay, so xy minus z equals 0, fantastic. We'll define capital F as being xy minus z. We can find all our partial derivatives, and when we do so, we can evaluate them at the point. All right, so we get partial derivative with respect to x is -3, partial derivative with respect to y is -2, and the partial derivative with respect to z is -1. But remember, in these direction numbers, we don't have to take negatives. We can multiply them by a -1. They're all, plus or minus a constant. So let's make that constant work for us. We're going to multiply by -1 and use our direction numbers of 3, 2, and 1. For the tangent plane, that becomes 3 times x minus a -2, so x plus 2, plus 2 times y minus a -3, so y plus 3, plus 1 times z minus 6. When we simplify it out, we'll have 3x, 2y, z. Here we have 6 and another 6. That's 12 minus 6 makes 6 on the left-hand side. Want to move it to the right, it becomes a -6. Fantastic. Here's the equation of a plane. But remember, we have our direction numbers. We have x plus 2, or x minus a -2, divided by the direction number, divided by 3. As long as the direction numbers are non-zero, then these equations, there are the set of symmetric equations for the normal line. Y plus 3 divided by 2. Z minus 6 divided by 1. Remember, we're using the positive values of these because we can use any constant multiple. All right, those symmetric equations, man, that would have been nice to remember on Chapter 12 quiz, wouldn't it? That's all right, you got this, you got this. Make sure you write them down in your notes for the Chapter 13 quiz. They came from Chapter 11. Make sure you review them, understand them before your next quiz as well. All right, so let's find a set of parametric equations for the tangent line to the curve of the intersection of x squared plus y squared equals 2 and z equals x at the point 1, 1, 1. All right, so we're going to define two functions. All right, we want to know the intersection. So x squared plus y squared minus 2 is going to be our capital F. We're going to take x minus z to be our capital G function. So we're going to look at two functions, f and g. We're looking for this intersection. We're going to use the cross product. So the gradient of f, right, we'll take the partial derivative with respect to x. So we get 2x times I. The gradient is a vector. The partial derivative with respect to y is positive 2y times j. Partial derivative with respect to z, there's no z, so there's no k term. At the point 1, 1, 1, the gradient of f is 2i plus 2j. We're going to do the same thing with our gradient of g. Notice, though, that the derivative of x is 1. There's no derivative of y, so we do not have a j term. And the derivative of z is -1, so we have a minus k. And I minus k doesn't care what's going on with x, y, or z. There's none in here. It's just I minus k. So we find the cross product, so we can find our intersection at these evaluated versions. We have ijk, 2, 2, 0k, 1, 0j minus 1k. As we do the cross product, it simplifies to, and I encourage you to do the work that's contained in this equal sign. It comes out to minus 2i plus 2j minus 2k. And if we factor out a minus 2, because 2 out of the 3 terms are negative, if we factor out a minus 2, we're left with I minus j plus k, and we could use the direction numbers 1, minus 1, and positive 1, right? Plus or minus a constant, they're all the same direction. So what would our line be? This would be x minus 1 over 1 equals t, so x equals 1 plus t. Y equals 1 minus t. z equals 1 plus 1t, right? 1 plus 1, these are all 1s. This one's a negative, so it's point plus direction number times t, y coordinate of the point plus direction number times t, z coordinate of the point plus direction number times t. Whew, that was hard on my brain. All right, but remember, that's going back to chapter 11. Review it. We're going to be using it. Another use of the gradient of capital F of xyz is to determine the angle of inclination of the tangent plane to a surface. The angle of inclination of a plane is defined as the angle theta in the first quadrant between the given plane and the xy plane as shown. I think of this as one of those, all right, so I'm a Ninja Warrior fan. It's the way it is. You could think of it as a mascot at a basketball game, right? They have that bouncy mat set up at a specific angle, get the perfect, right? They need mathematicians to figure out where to put this based on their jump and everything. So in the xy plane, right, theta is the tilt. Notice that k is parallel to z. K is normal to the xy plane. Because of this, we can use the formula for the cosine of the angle between two planes to conclude that the angle of inclination of a plane with a normal vector n is the cosine of theta is the magnitude of the normal dotted with k, right? K because it's normal, over the normal of n. The magnitude of n, sorry. Normal vector n dotted with k divided by magnitude of the normal vector. Oh my goodness, let's just do an example. Find the angle of inclination of the tangent plane to the surface given by 3x squared plus 2y squared minus z equals 15 at the point 2, 2, 5. So the first thing I'm going to do is I'm going to define my capital F. My capital F, I'll subtract capital F functions. I'm going to subtract the 15 from both sides. Once I have my function, capital F of x, y, z, I want to find the gradient. So I'm going to take the partial derivative with respect to x, 6x, times I. Partial derivative with respect to y, that's 4y, times j. And the derivative of z, which is minus 1, times k. Constants, derivatives, gradients, don't care about constants. If we evaluate our gradient at x equals 2, y equals 2, and z equals 5, we'll have 6 times 2 is 12, 4 times 2 is 8, negative 1 still doesn't care what z does. Now, the normal dotted with k, we know that this gradient is normal, right? It's normal to the surface. So we're going to use a dot product, but check it out. When we do dot product, right, we have 12i plus 8j minus k, and I'm dotting it with k. So I'll have 12 times 0, 8 plus 8 times 0, plus negative 1 times 1. Well, negative 1 times 1 is 1, and the absolute value of negative 1 is 1. Now I need to find the magnitude of the gradient of f. 12 squared is 144. 8 squared is 64. 144 and 64 is 208. Negative 1 squared is 1. 208 plus 1 makes a square root of 209 in our denominator. Look at that mental arithmetic. I can't say words, but numbers I got. So if cosine of theta is 1 over the square root of 209, we can use the inverse cosine in degree mode to find that this is approximately 86.03 degrees. Oh, all right. Alternative formula for the angle of inclination using the partial derivatives. Wow, that one looked weird at first, but that's a correct version. Just like in 2 dimensions, the gradient is normal to level curves. The gradient is normal to level surfaces in 3 dimensions. If capital F is differentiable at an initial point, and the gradient at the initial point is non-zero, then the gradient at the initial point is normal to the level surface through the initial point. All right, this is our last example, so move those captions up to the top of the screen if you need to. I can't scroll down anymore. Find the point or points on the surface given by z equals 3x squared plus 2y squared minus 3x plus 4y minus 5 at which the tangent plane is horizontal. First thing we do is always form our function capital F. We're going to subtract z from both sides. Now we find the gradient. All right, in the gradient, we look for the partial derivative with respect to x first. Derivative of 3x squared is 6x. The derivative of a minus 3x is minus 3. And there are no other x terms. Those are times I, right? Vector I. Vector dimension I. Now we look at the derivatives of y. Partial of y, we got 4y plus 4. Partial with respect to z, oh, look at that. It's a negative 1 times k. Now, we know if I want the tangent plane to be horizontal, my gradient has to be 0, right? It's a slope. So 6x minus 3 has to be 0. 4y plus 4 has to be 0. That's not going to tell us anything. If 6x minus 3 equals 0, then 3 divided by 6, x will be a half. If 4y plus 4 equals 0, subtract 4, divide by 4, y equals a negative 1. Now, we don't have any information about z over here, nothing whatsoever. But we do know what z is equal to. So taking z, substituting 1/2 everywhere we see an x, a negative 1 everywhere we see a y, we can find our z value, negative 31/4. And we have found the point on the surface given by z at which the tangent plane is horizontal. We found where there's a rise, right? I mean, think about what this correlates to in our 2 dimensions. Where's the tangent plane horizontal? It's a nice level surface right there. All right. Once again, I'm sorry that we had to do this by recording and not in person. But if you have questions, I'll be on my computer as I'm able. I'm gonna be answering questions. I'm gonna get here every day, at least twice a day. All right. Thanks for listening.